So we're now on to part B of question 2 from the second in-course exam, and this also has to do with vectors. So part B says that straight lines L1 and L2 have equations as follows. L1, and we're given the vector equation of L1 and L2, and part 1 of the question wants us to deduce the direction vector of L1, write out the parametric equations of L2, and then calculate the point of intersection of L1 and L2. So we'll start by writing down the equation of L1. So for L1, we have R1 is equal to, but of course write it using column vector notation. So this is equal to, or the column vector form, 1 plus 2t, 6 minus 3t, and then 4 minus 5t. So the first part of the question basically wants us to deduce the direction vector of L1. Now if you recall, generally for the vector equation of a line is given in the form R is equal to A plus lambda m, where A is a point on the line and m is the direction vector. So if we basically express this in that form, then basically what we have is this. We have R1 equals, now 1, 6 and the 4, then those basically will be the coordinates of the point A on the line, and so we can separate it from the other term. So this becomes 1, 6, 4, and this leaves us with plus 2t minus 3t minus 5t. But of course the parameter is t, and if we take the t outside the bracket, then this becomes R1 is equal to 164 plus t 2 minus 3 5. And then if we compare to the standard vector equation R is equal to A plus lambda m, we clearly see that 164, that represents a point on the line, and of course t is a parameter indicated by lambda, and the direction vector would be 2 minus 3 5, and therefore the direction vector of R1 is 2 minus 3 5. Alright, so that is the direction vector of R1 as required in part 1. Now let's look at part 2. Part 2 wants to write out the parametric equations of L2. Now let's write down the vector equation for L2. For L2, we have R2 is equal to 5 minus 5, 3, plus the parameter which is P times 1 minus 4, 2. Now basically we can represent R2 by general point. We can say this is equal to x2, y2, z2. And this would be equal to 5 minus 5, 3, plus, if we multiply the terms inside the column vector by p, then this becomes p minus 4p, 2p. And then we add the corresponding terms, and this becomes x2 is equal to 5 plus p, y2 is equal to minus 5 minus 4p, and z2 is equal to 3 plus 2p. And these are the parametric equations for line L2. So we found the parametric equations for line L2, and we've also found the direction vector of L1. And now basically we need to find the point of intersection of L1 and L2. Now to do this, we'll also need to write the parametric equations of line R1. Now if we let R1 be x1, y1 and z1, then this basically gives us 1 plus 2t, 6 minus 3t, 4 minus 5t. So x1 will be equal to 1 plus 2t, y1 equals 6 minus 3t, z1 equals 4 minus 5t, and these will form the parametric equations of line L1. So these are the parametric equations of line L1, and of course you can see the parametric equations of line L2 as well. Now if there is a point at which these two lines intersect, then it basically means that there's some common point which satisfy these three equations. What exactly does that mean? It means that basically x1 must be equal to x2, y1 must be equal to y2, and z1 must be equal to z2. So say if the lines intersect, there is a common point such that x1 is equal to x2, y1 is equal to y2, and z1 is equal to z2. So therefore, applying this, what we have is that, so for x1, 1 plus 2t is equal to x2. So we have 1 plus 2t is equal to 5 plus p. We'll call it equation 1. For the z, for the y rather, we have 6 minus 3t. That is equal to minus 5 minus 4p. And we'll call it equation 2. And lastly, 4 minus 5t is equal to 3 plus 2p, and we call it equation 3. So basically, now we have three equations in t and p, and we'll solve the equations simultaneously. So we'll take two of the equations together, solve them simultaneously for p and t, and then basically substitute the values of t and p into the third equation to see if it actually satisfies the third equation. So let's focus on equations 2 and 3. And let's examine the coefficients of t and p in both equations. In equation 2, the coefficient of t is minus 3, while in equation 3, the coefficient of t is minus 5. In equation 2, the coefficient of p is minus 4, whereas in equation 3, the coefficient is 2. So if we want to solve the two equations simultaneously, we can eliminate p if we multiply equation 3 by 2. Multiplying equation 3 by 2, this will become 4p. Then when you add it to equation 2, then the p will be eliminated. So say equation 3 times 2 gives us 2 times 4, that is 8, minus 2 times 5, that is 10t, equals 2 times 3, that is 6, and 2 times 2p plus 4p. And despite this basically being the same equation, we'll call it equation 4 because it looks different. Right? So let's call it equation 4. Then now to eliminate p, we'll add equation 4 to equation 2. So equation 4 plus equation 2, that gives, so we have 6 plus 8, that gives us 14. Then we have minus 3t plus minus 10t, that gives us minus 13t. Then we have minus 5 plus 6, that gives us 1. And lastly, minus 4p plus 4p, that gives 0, and there's no need to write plus 0. So now we have eliminated p, and now we can solve this equation for t. So we get minus 13t is equal to 1 minus 14, minus 13t is equal to minus 13, and therefore t is equal to 1. Now that we found the value of t, we can then substitute it into either equation 2 or 3 to find the corresponding value of p, since those are the two equations we basically solve simultaneously. Now let's put t equals 1 into equation 3. So we have 4 minus 5t is equal to 3 plus 2p. And so we have 4 minus 5 is equal to 3 plus 2p, minus 1 is equal to 3 plus 2p, minus 1 minus 3 is equal to 2p, and so we have minus 4 is equal to 2p, which therefore means that p is equal to minus 2. So p is equal to minus 2 and t is equal to 1. So those values of p and t satisfy equation 2 and 3. Now we must check if they also satisfy equation 1. So according to equation 1, 1 plus 2t is equal to 5 plus p. Substituting t equals 1 and p equals minus 2 gives us 1 plus 2 times 1 is equal to 5 plus minus 2. 1 plus 2 is equal to 5 minus 2. 3 is equal to 3. And therefore, what does it show? It shows that t equals 1 and p equals minus 2 also satisfy equation 1, which basically means that they satisfy all three equations. And this, of course, tells us that then there is indeed a point of intersection. Now, to find that point, all we need to do is to either take the parametric equations for line 1, which are in terms of t, or the parametric equations for line 2, which are in terms of p, and substitute t equals 1 to find the x, the y, and the z value, or substitute p equals minus 2 into these equations to find the y value. But either case, you should get the same sets of values. So let's use the parametric equations for line 1. So we get x is equal to 1 plus 2t, which of course you have to found to be equal to 3. So x is equal to 3. Y is equal to 6 minus 3t, which is equal to 6 minus 3, which is equal to 1. And z is equal to 4 minus 5t, which is equal to 4 minus 5, which is equal to minus 1. 6 minus 3 rather, that is equal to 3. So 6 minus 3 is equal to 3. And therefore, the point of intersection is 3, 3 minus 1. So that's the point of intersection of line 1 and line 2. Now, as I said before, we could have also, instead of substituting t equals 1 into the parametric equations for line 1, we could have also substituted p equals 2 into the parametric equations for line 2. And of course, we ought to get the same coordinates, the same x, y, and z values, but just to verify, we'll do it as well. So I'll just erase these. So basically what we have, these would be x equals 5 plus p, y is equal to minus 5 minus 4p, and z is equal to 3 plus 2p. So substituting p is equal to minus 2 into these equations gives us x is equal to 5 plus minus 2, that is equal to 3. Y is equal to minus 5 minus 4 times minus 2 gives us minus 5 plus 8, which is equal to 3. And lastly, z is equal to 3 plus 2p, which gives us 3 plus 2 times minus 2, which is 3 minus 4, which is equal to minus 1. And again, it proves that our point is correct, and the point of intersection is 3, 3 minus 1. So basically, well, this ends part B of question 2, and ends question 2, it is on vectors. So we managed to basically find the direction vector of L1, the parametric equations of L2, and also to find the point of intersection of L1 and L2.